Oke, silakan Anda presensi, linknya sudah ada di kolom chat. Ya, pada pertemuan kali ini kita akan membahas masalah topik baru, yaitu tentang ADC dan DC. Oke, kita mulai pokok bahasan dulu mengenai ya. Oke, yang pertama itu adalah DAC atau Digital to Analog Converter. Artinya inputnya digital. Oke, kalau digital to analog, kebalikannya inputnya analog, keluarnya adalah oke. Biasanya nanti kalau Anda belajar tentang sistem embedded, ya Anda akan menemui ya, yang biasanya ada itu adalah ADC, analog to digital converter. Oke, kalau yang DAC itu biasanya jarang digunakan di sistem embedded, maka di sistem embedded jarang ada di DAC. Oke, kita lihat dulu video terkait dengan DAC dan DC. Oke, kita melihat dulu terkait dengan DAC, digital to analog converter.
Hello, and welcome back to the Learning Circuit. We're learning about converting analog and digital signals. In the last pair of videos, we learned about ADCs, analog to digital converters. Now it's time to learn the flip side of that conversion and learn about DACs, digital to analog converters. Analog signals resemble smooth, continuous waves and can be infinite voltages within a certain voltage range. For example, 0 volts to 9 volts. Digital signals are typically on or off, high or low, represented by a 1 or 0. While digital signals can represent a number of voltages within a range, that number is limited by the resolution of the device interpreting or producing the digital signal. The world around us is analog, but the technology we use is often digital. So we need a way to make our technology communicate with the real world. To take in information from the world, analog sensors can be used to interpret light, sound, movement, temperature, and more. ADCs can be used to turn those analog inputs into digital signals for processing. There are many cases where output signals can be digital. However, since the world is analog, sometimes those digital signals must be converted back to analog in order to be used. This is when we need a digital to analog converter. A digital to analog converter, or DAC, takes a binary number and converts it to an analog voltage that is proportional to the binary number. To understand how DACs work, we can look back to one of the circuits we learned about with op-amps, a summing circuit. This circuit has multiple inputs, each run through a resistor, to one input of the op-amp. Another resistor connects the input with the output, creating a negative feedback loop. In this circuit, the output voltage is the inverted sum of all the input voltages. Typically, the resistor values would all be the same. If they were different, it would change the weight of each input voltage and how it affects the output, and the output voltage would not be a true sum. In a summing circuit, with all the values the same, the inputs are balanced. But for a DAC, we actually want the values to be unbalanced. The op-amp circuit we need for digital to analog signal conversion is called a binary weighted input DAC. To understand how this circuit works, we should start by reviewing some bits about binary. Binary is base 2, meaning it counts up to 1, then rolls over to the next place. 0, 1, 0, 1. Every time the number rolls over, another bit is added. If we continue counting up in binary and comparing those numbers to their decimal equivalent, we can see which decimal number each place represents. 0, 2, 4, 8, 16, and so on. You can see that each bit is twice that of the previous bit. In a binary weighted input DAC, also known as an R divided by 2n R DAC, each input has a different resistor value. Since each voltage input represents a binary bit, the resistor values are adjusted accordingly. For example, if V1 uses a 1 kilo ohm resistor, the next input would use double the resistance. So V2 would use a 2 kilo ohm resistor, V3 4 kilo ohms, and V4 8 kilo ohms, just like the values for each binary bit. See how these align with binary bit values? When a voltage input is pulled low, that bit outputs 0. And when the voltage input goes high, that bit outputs a 1. All the digital input bits are simultaneously applied to the DAC, meaning the circuit can interpret a whole binary number all at once. The differing resistor values give each input a certain weight, which translates to evenly divided voltages at the output. You can see that as the binary number counts up, representing input voltage changes, the output voltage increases consistently. The number of voltage steps is defined by the resolution. The resolution is set by the number of bits, which is set by the number of inputs. Adding more inputs increases the resolution. With this DAC, as the resolution increases, a larger variety of resistor values are needed. Due to the manufacturer's tolerance of the resistors, the higher the values and the wider the range of values, the less precise they are, and the less accurate the signal conversion is. The next type of DAC has a resistor structure that helps improve upon those issues. The inputs in this type of DAC use an R2R resistor layout referred to as a ladder. Only 2 different resistor values are needed to make this ladder. Connecting to one op-amp input is a voltage divider connected to ground. At each resistor junction connects a voltage input through a resistor value of 2R. And there's still a negative feedback resistor connecting the op-amp input and output with a value of 3R. If I simplify the circuit down, starting with 1 bit, you can see how the op-amp input voltage is divided. Adding another bit, the values change. And again with 3 bits, and with 4 bits. Once again, note how the voltage divider values resemble the values of each binary bit. One of the benefits of this type of DAC layout is that 2 resistor values could be used to build the ladder. Or, for 2R, 2 resistors could be placed in series to create that value, requiring only 1 resistor value needed to build the circuit. Another way to achieve digital to analog conversion is by using a process called PWM, pulse width modulation. PWM uses digital pulses, varying the timing or duty cycle between high and low signals. The time off versus the time on defines the duty cycle. By varying the duty cycle and switching frequency, an analog output signal can be produced by averaging the voltages of the input signal pulses. With any DAC, having a higher resolution will yield a more accurate conversion. As we saw with ADCs, lower bit resolution DACs may not keep up with rapid frequency changes, while higher bit resolution DACs can produce a more accurate conversion of the binary digital signal to an analog wave. Something to keep in mind is that once an analog signal is converted to digital, it can never truly be as purely analog as it was, even if converted back. The process of converting digital to analog still uses digital steps, where the signal increases or decreases in voltage ever so slightly. Given a high resolution, comparing an original analog signal and a converted analog signal, the difference is often imperceptible. However, looking very closely at the signals, the converted digital signal will always have steps, even if they are extremely small. DACs cannot create a perfectly smooth output wave as a true analog output. This is where your audio purists love to geek out. All those vinyl record collectors have a point. Vinyl records are embedded with a truly analog signal wave that is played by the record player needle. However, virtually every other form of music recording is at some point converted to digital, and will always have that little bit of compression problem where the output wave will never truly be smooth. Music isn't the only audio application for DACs. They're also used in telecommunication. When you talk into a telephone, the microphone detects the analog signal that is your voice. It is then converted to digital to be transmitted long distances, and then converted back to analog to be played out a speaker on the receiver's phone. DACs are also used for video processing. Many modern TVs and video displays use digital inputs like HDMI that don't require analog conversion. However, on older video displays, you can find RCA jacks with one yellow composite or 3 red, green, and blue component video inputs that are analog. These require the video output device, such as a DVD player, to contain a DAC. Lastly, DACs are commonly used in motor controllers, converting the digital signal from microcontrollers into an analog signal used to vary the speed of the motor. This is often done with PWM. Well, that's all I've got about DACs. For now. Remember to keep an eye out for my next video where I show you a practical application of using a digital to analog converter. If you have any questions about what I talked about in today's video, remember you can always find me as Maker Karen on the Element 14 community on element14.com/The Learning Circuit. Happy learning!
Ya, sekarang kita masuk ke cara kerja adisi.
Hello, and welcome back to the Learning Circuit. I'm Karen, and today we're going to learn about analog to digital converters. Let's start by making sure we have a good understanding of analog versus digital. Many of our electronic devices are digital circuits that use analog sensors to interact with the real world. These analog sensors provide a signal that can register any value between 0 volts and a given maximum voltage like 5 volts or 9 volts. Digital signals are expressed in binary. As we've learned before, binary is a series of ones and zeros, with each number place counting up to 1 and then rounding over. We can compare digital to a light switch, turning the light either on or off, whereas analog would be like a dimmer switch, able to set the light level to any brightness between its maximum and off. However, digital signals are not limited to just on and off. Digital devices are often capable of counting to multiple places in binary. Every time the number increases and gains a new place, it gains a bit. You've probably heard bit before, like with vintage 8-bit video games like Atari or the original Super Mario Bros., or like my shirt. An 8-bit number would have 8 places, or bits. This can also be expressed to 2 to the 8th power, which is 2 multiplied by itself 8 times, a decimal equivalent of 256. Looking at binary values, expressed in ones and zeros, as an exponent of 2, and as a decimal number, we can see that when a binary number gains a bit, the decimal number tells us how far it counts in order to gain that bit. This decimal number is the resolution. Binary starts counting at 0, so while 8-bit has a resolution of 256, the highest 8-bit number is 255. Analog to digital converters start as low as 8-bit and can be found as high as 32-bit, but are most commonly 10, 12, 16, or 24-bit. Looking at the waveform of an analog versus a digital signal, an analog signal would have a smooth, continuous slope representing how the signal can be infinite values between 0 volts and the maximum voltage. The waveform of a digital signal changes in steps, with a finite number of steps equal to the ADC's resolution, divided evenly between 0 volts and the maximum voltage. The signal change at each step goes low to high or high to low. ADCs can convert analog to digital signals in a variety of ways. In the first type of ADC, we can see how a comparator is responsible for each step change. Previously, we've learned that a comparator has 2 inputs. If the positive input is greater, the output is a high 1. And if the negative input is greater, the output is a low 0. A flash, or direct conversion ADC, uses a number of comparators for parallel encoding. Here is a 3-bit ADC having 3 output pins, 1 for each bit. Since a 3-bit ADC counts from 0 to 7, 7 comparators are needed. Each comparator connects to the analog input signal, as well as a voltage divider that splits the reference voltage. The comparators process their signals simultaneously, each outputting a 0 or 1 accordingly. The comparators feed into a logic circuit, which processes the data and outputs the 3-bit binary number. The analog input wave is converted to a 3-bit digital wave. This style of ADC is great for how fast and efficient it can convert the signals due to its parallel processing. However, given the large number of comparators needed, and since each bit requires its own output pin, chips can quickly become large and expensive to manufacture. To solve the problem of requiring an output pin for each bit, rather than having numerous parallel outputs, many ADCs run the output signal through a shift register, which then sends serial data out a single output pin. The next style of ADC is called a digital ramp or ramp compare. With this style of ADC, a free-running binary counter produces a sawtooth wave fed into a digital to analog converter. The sawtooth signal gets compared to the analog input signal, and when the signals match, the corresponding binary number is output, the ADC's timer resets, and the sawtooth starts over. The sawtooth always starts from 0, so the lower the signal, the faster the signals match, but the higher the signal, this inconsistency in update frequency can be problematic in certain applications. The next type improves upon the ramp model, being slightly faster due to its special counter circuit known as a successive approximation register, or SAR. This ADC starts with its most significant bit, comparing it to the analog signal. If the signal is less than or greater than, the counter adjusts the bit values up or down accordingly, continuing to compare bits down to the least significant, narrowing the range until the signals match, then starting over again at 0. The next type of ADC tracks the previous output signal, constantly comparing it to the analog input signal. Depending on if the input signal is less than or greater than it was previously, the counter adjusts up or down. This method is much faster since the counter never has to reset. The downside to this type of ADC is that it experiences a phenomenon informally known as bit bobble. Due to the fact that the output updates on every single clock pulse, the signal will always change at least slightly up or down. The next type of ADC compares similarly to a ramp ADC, generating a sawtooth wave. But instead of using a digital to analog converter, This slope or integrating style ADC uses an op-amp circuit called an integrator. A slope ADC uses the analog input voltage to charge up the internal capacitor, and then measures the time it takes to discharge across the internal resistor. However, the rate of integration and the rate of count are independent of each other, so over time they inevitably drift and the ADC becomes less accurate. A slight variation on this model is the dual slope ADC. Its integrator circuit is driven positive and negative in alternating cycles to ramp down and then up, rather than being reset to 0 volts at the end of each cycle. A few other types exist, like a delta-encoded or sigma-delta ADC, but are either too complex or rare enough to go into detail about how they work. How the ADC processes signals will affect its step recovery time, an important factor to consider when selecting an ADC. Step recovery is a measure of how quickly an ADC changes its output to match a large, sudden change in the analog input. When choosing an ADC, you'll also want to pay attention to resolution. I mentioned before that ADCs most commonly are 10, 12, 16, or 24-bit. Note here the resolution differences between those chips. The more bits, the higher the resolution, the more accurate the signal conversion. Think of it like video resolution. In full resolution, this video is 1920 by 1080 pixels, or 1080p. Changing the video resolution down to 720p, for the video to be clear, it gets smaller. But zoomed in, you can see the quality looks degraded. Let's make it even more pronounced and change the resolution to 240p. Blech! That looks horrible! Look at all those pixels! To make the video look clear, look how small I would have to get. High resolution is definitely better. Hey! Let me out of here! Another factor to consider is sample rate. The sample rate is the frequency at which the ADC converts signals and outputs a new binary number. Sample frequency is measured in hertz and can be found in the datasheet, sometimes labeled as clock frequency. For applications with slow-changing signals, a low or slow sample frequency would be sufficient, like measuring how much water is in a rain gauge. However, with signals that change rapidly, like audio frequency signals that vary several thousand times per second, the converter needs to be considerably faster. The input signal frequency must not surpass what is called the Nyquist frequency. This is typically about half the sample rate. If the input signal frequency is too great, an effect called aliasing may occur. As you can see, this sample rate isn't fast enough to reflect an accurate analog to digital conversion. Ideally, the digital and analog waves should look alike. Analog to digital converters are commonly used in processing audio, such as in music recording, as well as in many scientific instruments, such as those that use radar or measure temperature, pressure, pH, or light intensity. How else can you think of using an ADC? Or do you already know because you've used one in a project? Maybe you've used one you didn't even realize it. Keep a lookout for my next video where I show one way to use an ADC. I'll tell you a secret. There's one in an Arduino! As always, if you have any questions or comments about what we learned in this video, you can find me, Maker Karen, on the Element 14 community on element14.com/the learning circuit. Happy learning!
Itu tadi adalah penjelasan tentang DAC maupun ADC. Nah, kita tahu alam yang kita tinggali, ya. Jadi semua alam itu basisnya adalah terkait dengan suara, ya, citra. Nah, itu semuanya basisnya adalah oke, di sini misalnya ada suara, Di sini ada mic, kemudian masuk ke microcontroller. Nah, di sini ada yang namanya materi. Oke, nah dari input yang analog ini, ya, jadi kalau situasi variabel-variabel di alam itu analog, suara, terus pemandangan, ya itu semuanya ada. Sedangkan nanti di dalam microcontroller itu semuanya diproses menggunakan sistem digital nomor satu. Maka di dalam microcontroller itu ada yang namanya shifting dari analog ke digital. Ada juga yang ini itu analog setelah proses, tetapi keluarannya adalah ini prosesnya digital, keluarannya adalah sebentar. Maaf, tadi ada jaringannya agak buruk, dia keluar sendiri. Kita lanjutkan. Jadi variabel-variabel yang ada di alam di sekitar kita, baik itu suara, cahaya, kemudian panas, nah, semuanya itu berupa besaran-besaran. Maka dalam sebuah sistem digital, sini kalau di input kita, ini adalah analog, ini analog. Nah, kalau kita punya microcontroller, komputer, itu adalah sistemnya digital. Nah, kalau kita ingin mengukur besaran di alam, maka kita menggunakan yang namanya sensor. Oke, input. Oke, ini adalah sensor. Nah, dari sensor ini kemudian masuk ke microcontroller. Dalam microcontroller di sini ada yang namanya ADC, analog to digital converter. Jadi dia mengonversi dari besaran-besaran analog ke besaran digital. Nah, kemudian ini statusnya adalah input sebagai input. Kalau kemudian statusnya sebagai output, nah, di sini ada yang namanya dac. Kita ke analog converter. Oke, di sini biasanya kalau Anda baca dengan microcontroller, ini adalah motor. Nah, dari sini kita bisa mengetahui kalau ADC itu adalah sebuah proses mengukur besaran analog, kemudian dikonversikan ke digital. Biasanya digunakan sebagai input, ya, sebuah sensor. Di sini ada sensor. Kemudian sensor itu mengukur besaran analog. Dari besaran analog kemudian dikonversikan ke bentuk digital. Nah, kemudian kebalikannya, kalau dac itu besaran-besaran digital. Ya, jadi di sini akan menjadi proses, kemudian dia akan diumpankan ke dac. Dari dac ini keluarannya adalah berupa sinyal. Nah, ini biasanya digunakan untuk mengatur kecepatan motor. Biasanya untuk kecepatan motor. Nah, kita mulai dulu dengan dac. dac apa toh? dac itu pakaiannya adalah ini sama seperti rangkaian equalizer, ya. Jadi kalau Anda sudah belajar tentang equalizer, ini adalah rangkaian equalizer. Rangkaian ini dinamakan apa? Rangkaian sebagai rangkaian penjumlah. Jadi di sini nanti kalau boleh Anda artikan sebagai pencampur, boleh. Jadi kalau di sini ada sinyal, ada suara, di sini ada suara, di sini ada suara, maka ketiga sinyal ini dijadikan satu. Nah, ini adalah proses DAC. Kemudian dari video bisa kita lihat juga DAC itu ada dua. Yang pertama itu adalah ya. Oke. Jadi ini adalah ya. Jadi ini adalah rangkaian penjumlah. Ini adalah op-amp, di sini ada rangkaian penjumlah, ini adalah rangkaian pengaturnya. Oke. Jenis yang pertama adalah R binary. Mengapa disebut R per 2? R kali R. Nah, di sini ini 1 kilo, 2 kalinya adalah 2 kilo, 2 kalinya adalah 4 kilo, 2 kalinya adalah 2 kilo. Oke, ini. Nah, yang kedua, materi dac. Oke. DAC ada dua. Nah, yang pertama adalah rangkaian R. Jadi ini adalah rangkaian pembagi tegangan sebenarnya. Nah, rangkaian R ini kemudian ada yang dinamakan sebagai yang kedua adalah rangkaian padat. Oke, yang ketiga adalah BWM ya. Oke, kita tahu bahwa kalau yang ini kelebihannya apa? Karakteristiknya adalah ya, jadi kalau yang bawah itu R, nanti atasnya lagi ya. Jadi yang di sini itu 16, ini 8, setengahnya ini setengahnya lagi, ini setengahnya lagi, ini setengahnya lagi. Di mana R-nya adalah oke, nilai R-nya adalah R, R, terusnya. Kalau ladder diagram, ladder dac itu R dan 2R. Oke, jadi di sini R, di sini 2R. Ini R, ini 2R. Kalau yang tadi itu ada R, ada 2R, 4R, 8R, dan seterusnya. Tapi kalau yang ladder itu cuma R dan 2R. Ya, keuntungannya cuma kita cuma membutuhkan dua jenis resistor. Nah, kalaupun satu jenis resistor, satu value, itu juga masih bisa. Ya, kalau satu ya ini ada dua, ini 2R, R, ini 2R, 2R, 2R. Jadi kalau untuk seperti ini pun itu adalah cuma menggunakan satu nilai R. Kalau yang di sini itu menggunakan banyak nilai R. R, 2R, 4R, 8R, 16. Nah, cara yang kedua, nah ini yang biasanya digunakan di microcontroller, itu menggunakan prinsip kerja BWM. BWM itu adalah sinyal. Nah, di sini untuk mengukur R-nya itu memakai cycle. Duty cycle itu apa? Itu adalah nilai 1 perbandingan nilai 1 dan nilai 0. Ini nilainya 1, ini nilainya 0. Kalau duty cycle-nya jadi satu sinyal itu punya seperti ini ya. Oke. Ini nilainya 1, ini nilainya 0. Oke, yang dimaksud dengan duty cycle itu adalah ini. Jarak nilai 1. Nilai 1 ini dibandingkan dengan nolnya, ya, dibandingkan dengan jarak sini. Jarak nilai 1 ini jarak dengan ada nilai 0. Sehingga di sini bisa dilihat ini 50-50 berarti 50 duty cycle. Kalau semakin lebar, ini 75%, ini 25, berarti duty cycle-nya 25. Kalau 25, maka yang nilai 1 itu 25, yang 75 adalah yang 0. Tetapi di sini itu nilainya tegangannya tetap ya. Ini tegangannya 1, jadi tegangannya 1 itu 5 volt, di sini adalah 0 volt. Oke. Nah, ini akhirnya DAC itu adalah ada dua jenis. Yang pertama itu menggunakan rangkaian R, yang disusun menggunakan R/2 atau menggunakan sistem. Yang kedua, sistemnya berbeda jauh, yaitu tentang BWM. BWM itu sebenarnya 0, 1, 0, 1, 0, 1, seterusnya. Tetapi berapa lama dia 0, berapa lama dia 1, itu akan menghasilkan tegangan yang berbeda. Jadi di sini biasanya kalau ini ada di sini ada yang namanya kapasitor. Ya. Kapasitor ini untuk apa? Biasanya digunakan untuk peretar tegangan. Di sini keluar, di sini ada. Jadi kalau dulunya tegangannya harusnya gini. Oke, jadi nanti diperhalus lagi sehingga bisa didapatkan gelombang yang oke. Itu terkait dengan DAC. Nah, sekarang bagaimana dengan ADC? Oke, ya. Jadi kalau ADC itu adalah tegangan. Kemudian kalau ini flash ya, kalau ada banyak kecepatannya tinggi, maka di sini ada komparator. Jadi kalau yang lebih ini adalah ada DAC, kemudian di sini ada flash ADC. Jadi di sini DAC dia memberikan tegangan, jadi tegangan referensi, kemudian dibandingkan dengan tegangan dari DAC-nya. Jadi di sini ada DAC. Jadi ini adalah kontrolnya, ini storage-nya. Nah, di sini jadi keluaran dari tegangan referensi yaitu berupa DAC dengan tegangan input itu akan dibandingkan. Kalau tegangannya naik, ya jadi sebenarnya kalau tegangan ADC ini adalah komparator, maka tegangan yang di sini dan tegangan yang di sini itu dibandingkan. Nah, ini input untuk tegangan. Nah, di sini ada yang namanya D. Di sini ada pintunya, ya. Ini digitalnya. Ini keluarannya analog, kemudian ini keluarannya juga analog, nanti akan dibandingkan. Kalau tegangan inputnya itu lebih tinggi, maka DAC-nya akan dinaikkan. Nah, kalau tegangannya lebih rendah dari DAC-nya, maka DAC-nya tegangannya diturunkan. Jadi nanti kalau ada yang seperti ini, kalau kemudian di DAC, itu terkait dengan ADC. Jadi kalau ADC itu di dalamnya ada rangkaian DAC-nya. Oke, ya, jadi bentuknya seperti ini. Kemudian di sini ada motor, di sini ada storage. Nah, ini sebenarnya dibandingkan. Ini adalah efek analog bentuknya dibandingkan dengan di sini. Oke, sampai sini ada yang mau ditanyakan? Kalau ada yang ditanyakan, kita lanjut tentang hal-hal yang terkait dengan ADC maupun DAC. Terkait dengan parameternya apa sih yang belum terperhatikan? Yang pertama itu adalah resolusinya, ya. Terkait dengan di sini, bit ini menunjukkan resolusinya, resolusi dari apa ya namanya, kepekaan dari ADC maupun DAC. Jadi semakin besar bit, kalau bitnya naik, maka resolusinya juga akan naik. Yang kedua itu adalah dari sisi kecepatan. Nah, kecepatan ini biasanya terkait langsung dengan ADC. ADC yang ada yang tipe lambat, ada yang tipe cepat atau tipe flash. Dua itu biasanya yang berpengaruh pada ADC maupun DAC. Ya. Jadi pokok bahasan kita sekarang itu adalah ADC dan DAC. Ada yang mau ditanyakan? Nggak ada? Oke, kalau nggak ada berarti sampai di sini. Silakan Anda on-kan kameranya.
Recording in progress.
Ya. Jadi seluruh pokok bahasan di dalam elektronika digital itu ada 3. Yang pertama itu rangkaian kombinasi, yang kedua itu rangkaian sekuensial, yang ketiga itu hubungannya dengan analog. Oke, gitu aja pertemuan kali ini. Kita akhiri aja. Terima kasih perhatiannya. Mohon maaf kalau ada yang salah. Kita akhiri. Selamat sore dan assalamualaikum warahmatullahi wabarakatuh.